Guys, I hope you guys have gone through my lectures 18 to 21. Okay, today we are going to do some tutorial for that particular topic. This tutorial actually covers uh, RH criterion and also Rooker-Lucas topic. Okay, it's about how to determine the stability of the systems. Okay, this is a past exam questions. So as you can see in figure 1 here, this is a control block diagrams that consists of controller K. There's our system G of S, output and input, right? Okay, basically in this kind of system, the performance and the stability of the output Y of S is determined by the value of K in the controller. Okay, so as we increase K values here, the output will change, not only the behavior or the response, but also the stability of the systems, because this K will change the roots of the closed loop system, right? If we derive the closed loop systems, the characteristic equation will have K in it, right? Okay, let's move on. Okay, first question, so state the stability of the roots Hurwitz criterions, then obtain the closed loop transfer function Ts and determine the gain margin, a range of K to keep the system within the stability limits. Okay, so if you see that this is a step before you can actually uh, fill up the RH table, you need to obtain the closed loop transfer function Ts from this open the systems here. Okay, then determine the gain margin to keep the system stable within the stability limit, right? Okay, the answer is on the right hand side here. So basically, okay, the first questions is asking about the stability criterions. The answer will be RH criterion guarantees that all roots in the characteristic equation are in LHP left hand plane, which is on the negative sides, and blah blah blah. All right, I think this you learned this in the previous topics. Okay, this is a table that we this is RH table that we need to fill up that table based on the CE here. CE is not, this is open loop, CE is a closed loop systems. We got this, and then we fill up this one, 14, 40 and K. Then the next row will be this one and 0 and K and 0. Okay, so now to keep the system within the stability limits, this column, the first column must be all positive. Okay, that means that, okay, to keep the system stable, first, not row, yeah, first column of the RH table must be all positive. So for this row, right, so we want to keep this positive, so K must be less than 560, right? If K is more than 560, this part become negative here, right? So that means the limit for this one to keep this row positive is K must be less than 560. Then for the next row, the same column, so we need to keep this positive value as well, right? So that means K must be greater than 0 in this case. So that means the gain margin or the range of K to keep this row positive is between 0 and 560. Okay, and then we can say that the gain margin is the maximum number of K minus the minimum number of K. In this case, we have 560. If K is not, if not 0, if K is, let's say, 100, that means the gain margin is 560 minus 100. That means the gain margin is 460, something like that. All right. Okay, fair enough. Let's move on to question B. Find a value of K that causes the system to operate at marginally stable, right? and determine the undamped natural frequency. So remember in our rough Rafferty criterion, we learn about how to make the system marginally stable, where the first row, right, this one have to be using the same table. We need to make this 0 so that we know that we can have these auxiliary equations here. So at that particular point, K is actually, the system is marginally stable, right? So that means at that particular K, which is 560, the system is marginally stable. Somewhere, the root is somewhere along the imaginary axis, okay? So hence, we know that K560, we have that auxiliary equations, which is 14s squared plus 560, right? Because we have to replace that K, yeah, we have to get the auxiliary equations here, 14s squared plus the K at that particular condition, which is 560, right? And then from there, we can find the roots where at that particular K, so it's exactly on the imaginary axis, right? So that means that system is marginally stable, okay? So the natural frequency in this case is 6.32 radian, right? Second. Yeah. So okay, let's move on to see state the stability criterion in the root locus. Okay, the stability criterion in the locus, as we discussed before, which is 1 plus kg of s equal to 0. This is the stability criterions. Okay, and then from there we have to find the magnitude and also the phase. Okay. Okay, it says that the root is said to be on the root locus if the summation of the open loop vector and the open loop zeros vector satisfy the following criteria. That is the stability criterion for root locus. Then we have all these equations here. Okay, and then using the root locus method, determine the stability, determine the parameters. Okay, again, whichever appropriate. Yeah, these parameters can be it depends on the system that we have. Some systems do not have certain things here, right? Certain parameters here. So we have to depend on the systems there. So in this case, we have to plot the root locus using rules method. Yeah, root locus rules method. Okay, there's a let me show you something. Okay, so there's parameters that we need to decide or determine from here. So which is number of branches, number of branch and infinite zeros, number of branch and at infinite zeros, asymptotes, breakaway point, break-in point, angle of departure, angle of arrival, imaginary crossing, and system stability. Okay, in previous lecture we learned about how to determine this value based on my lecture notes, right? Okay, number of branches is determined by the number of poles, which is in this case we have 3 poles here, right? One open loop poles, sorry. So it's determined by the number of open loop poles. Okay, open loop poles. Okay, so we have 3 there. Number of branches. That means if we have 3 poles, we have 3 branches of root locus. Number of branch and at finite zero That means we have a 0 here, right? No, there's nothing here. It's constant there. So we have no zeros there. So that means we have number of branch n at finite 0. So there will be none, 0, because there's no zeros there, right? Number of branches n at infinite zeros. So because of every pole has to find its own zeros, have to actually move approach zeros. So that means that triple will find 3 zeros at infinity, right? So we have 3 here. Okay. So that means if we have branch n at infinite zeros, we will have asymptotes, right? So our angle, basically, the asymptote will be 3 angle, because we need to guide these three branch towards the infinite zero using 3 angle, the directions. Okay, so asymptote we have 3 theta 1, theta 2, theta 3. So we have to find that breakaway point, because okay, you see that this is the poles are on the real axis. Okay, let me plot this here. So we have 1 here, 0, we have 1 here, -4, we have 1 here, -10, right? Based on this. Okay. Now we know that if this one is going to infinity, so we need to, it is possible for the root locus to break away from this. Okay, break away from this. We would say that breakaway point is yes. Okay, break-in point only happen when you have poles on the imaginary, somewhere imaginary, complex poles. Then you have probably find the zero along this line. Then you have break-in point. See, if you have that complex poles and uh, real zero, that means these poles will move towards the real line. So that means you will have that. Angle of departure also the same thing. Angle of departure only available when you have complex poles. Angle of arrival you can have when you have a complex zeros. Okay, so this one no, right? Break-in point, no. Imaginary cosine, yes, maybe yes. Okay, it depends. It could be no, it could be yes. It depends on the angle of departure, angle of asymptote angle. If the angle is straight, that means it won't cross this. Okay. System stability will determine later. Okay. Determine later. All right. So now we have this one. We need to find this. Okay. In order to find this, we need to use um, the okay. We need to use this the formula here, which is a real asymptotes equal to, you can see, you can refer to my lecture notes like this. Yeah. Okay, this one. So that means number of finite poles number of finite poles we have 3. Okay, not 3. Finite poles means the number, the poles. Okay, so we have as we have 0, minus, which is plus, minus 4, plus minus 10, right? That is the summation of finite poles. Zeros, we have zeros there. Okay, so that's 0 minus 4 plus minus 4 plus minus 10, 0. So that means our finite poles minus finite, the number of finite poles, we have 3 minus 0, 3 minus 0. So we have about minus 14 over 3. So equal to minus 4.67. So this is the asymptote point. So we can actually place somewhere minus 4.67 minus 14. Okay, which is somewhere here, right? I'll use red pen, minus it, somewhere there. Okay, there's a point. So now we need to find the theta 1, theta 2, theta 2, theta 3. We need to use this, right? This one, which is theta A equals to 2k plus 1 pi over a number of finite poles, number of finite zeros. So 2k plus 1, 180, put it there, then 3 there. 3 is the same thing like this. Okay. Then because theta 1, we have to start with k equal to 0, theta 2, k equal to 1, theta 3, okay, k equal to 2. Okay, theta 1, k equal to 0, k equal to 0, there's 0, 1, 1, that means 180 over 3, so 60 degrees. Theta 2, 2, 4 plus 5, 5, 180 over 3 equal to 5 times 60, 300. Okay, and then theta 3, 3, 6, 7, 7, 180 over 3, so 7, 60, 120. Okay, all right, this angle, we need to draw it. Okay, we need to draw it here. So 60 is here, so 300, this is theta 1, theta 2 is 300, which is minus 60 there, theta 2, theta 3 is 420, which is 300, 420, it's equivalent to 360 plus 180, right? So it's 180 there. So that's theta 3. Okay, okay, I think I got the wrong value there. Okay, let me show you this. This is k equal to 1, supposed to be 1, 2, so 3 here. 3, supposed to be this one, 180. Okay, 3. It's 2, 4, 5. So this is supposed to be 300. So this is theta 3, this is theta 2, 180. So okay, yeah, 60, 180, 300. Okay, sorry, my mistake. Okay, that's the asymptote. Now you have this line here. You know that this is the directions to find the zeros from this. Okay, so we can simply, so the rules is symmetrical. We can actually move these directions here and move towards this. So this is our first branch. Second branch is going to this direction. Okay, the third branch. Okay, let me draw this. So it's basically from here, then moving to that direction. This one from here, meet that point. This is, we call it breakaway point. Okay, this is a breakaway point. Okay, so this one is going to that direction. So if you see that, the answer would be, look something like that. So the blue one is going this direction, the green this direction. Okay, from here we can see that, okay, there's a k value that will cause the system to be on this side, the roots, okay, on moving to this side. But this one is okay, it's going to this side, is forever stable, but at least one of the roots is going to this side, the system will be unstable, right? So if we determine from that, the previous answers there, 560 is when the k is here. So the poles, okay, the roots of the closed loop systems, when it cross this at this point, the k at that particular point is 560. So as k start from 0 here, but as we increase k values, okay, the root locus, as we increase the k value from 0, the closed loop systems, okay, the roots of the closed loop system actually move to these directions, and then all the way to infinity as k increases, right? But okay, to keep the system stable, that k must range from 0 until 560 as we calculated before. So that is the margin for the system to be stable, right? Okay, now we know that's the point where the systems, go back to the questions, we need to find the break-in point in this case, right? Yes, break-in point. And then the system stability, we need to say that the system is stable for the k from 0 to 560. Okay. So imaginary crossing is this root locus will cross at that point, at this point here, which is 6.32. So if we use the MATLAB to solve it, we can find these poles is 6.33, is about that point. Yeah? 0 plus 6.32i here. I cannot get the exact point here. So it's supposed to be 0 real. There's no component real there. So it's very close to that. So that means our calculation is correct. And then, okay, break-in point. Okay, how to calculate the break-in point is that we have to use the formula because okay. So right now we have this root locus already. It's here like this, right? So we know that the breakaway point will be around here between -4 and 0, right? So how do we calculate this? Because we know that from this kg of s equal to -1, right? So because we want to make sure that the value that cross this real axis, right? Instead of using s as an arbitrary a point, we have to limit that as a real number. So that means we have to use as a real number equal to -1. Okay, so that makes our system kg of real numbers. That's okay. By the way, our system g of s equal to 1 over s cubed plus 12s squared plus 40s, right? After you multiply that open loop systems, so the system becomes, you just replace s with this sigma, then we have 12s squared plus 4s. Okay, no, sorry. Okay, so right now this is 1 over, right? So it is minus plus 12 plus 40. 4s or 40? 40, 40, 40, 40. Okay. Okay. Okay, now we have that. Then we have to differentiate dk over d sigma so that we can find a curve that actually intersect with the line, right? That has this, that we can find the equal to 0. Okay, so dk over d sigma equal to minus 3 sigma squared plus 24 sigma plus 40. Okay, so now we have this, we need to find the roots of this, right? That root becomes basically okay, we will find some based on these equations. If we find the roots, that root is actually here, right? So this is first root, the second root, or the value that we have, right? So it will be somewhere there. Okay, now I'm using this online factoring tools. You can use this. Okay, 3x squared plus 24 okay, and then s plus 40. Okay, let's give you the answers. Three x plus 40. Sorry, this is not s. Okay, equals, and we have something like this, right? So how about we put negative here, put negative there, negative there. Okay, sorry, okay, it becomes slightly because there's negative here. Okay, that's the point. Yeah, the point that intercept is around uh, 1, 2, 2 point something, minus 2 point something there, right? So that is the point, the first point, the second point. So because that break-in point happened in between 0 and 4, we consider this point, okay, 0 and 4, we consider this point is a valid point there, right? This one we just ignore it, just take this point. Okay, that is our break-in point. I think what is the next question? Then place the open loop further than 0 and root occurs and right. Okay, this is the answers, and then we have to specify the location of this one, the break-in point. This the points here, the J5 point something, right? Um, J 6.3, sorry, 6.32, 6.32 there. The K at this point is 560. Okay, that's all. I think hopefully this helps. Thank you very much.